All right. So a couple notes about the project for next week. I've sent out the link to both articles. It'll be, so basically, you're gonna do sort of like a poster presentation. You're gonna kind of condense your project down into something you would put on a poster. And then yeah, basically. I attached a link to a site that's got some different templates that you can choose from. The sort of whatever fits best. Let me find I have the uh, basically your job is going to speak to explain your article, teach the material basically. I think both of you picked stuff that has new mechanisms we haven't seen. So you're basically just going to walk through the mechanism. It's going to be, just digging deep to explain everything. You're going to be the expert on that paper. And so you don't have to use a poster format for it, but I find it works the best because then everything is on one slide. You don't have to flip through slides and things like that. And then you can zoom in on relevant figures and things like that. I'd rather do it more as a PowerPoint slides presentation. You can do that.
And I started making it as
That's fine then. Especially since we're kind of doing this last minute, feels like we're doing it next week. So if you've already started breaking it down that way, that's totally fine. That's the way I present, so probably have, because I think it works all right. And yeah, it's just gonna be, it'll probably take, I'm not gonna put a hard time limit on it, but I would anticipate 10 to 15 minutes. If you go anything, you'll probably go a little bit over, and we'll do it during lab next week, or we'll probably have on Tuesday. We'll have a light lecture probably on Tuesday, because we have about 25 more slides to get through this last chapter, and then next Thursday we'll be reviewing. So you'll have some time to get ready, and then we'll do the presentations at home in lab. It'll be short because it's going to be and that's just the luck you get having a small class. And then Thursday will be a review day, and next we'll pull up the exam schedule, double check before I say something wrong. No, I'm not gonna say it until I check. Final exam schedule. And I think we actually have Tuesday or Thursday, because I don't think we have there's no conflicts with this time slot. 2-hour class. But with that in mind, let's double check when it's scheduled. We can talk about that, the final timing as well next Tuesday when everybody is around.
next Tuesday is probably when we're gonna get the review.
Get the review sheet, yeah, it's definitely a focus on, it'll be comprehensive in the sense that you still have to know how to draw a mechanism. I still expect you to remember the basics of all the stuff, that's gonna focus on the substance of it. It's not gonna be a full comprehensive of the entire year or anything like that. Although if you do go take a standardized test, vocab, it will be all of it. So that just involves a lot of reviewing. Or to save it. That's why I want to open it. they uploaded the final exam schedule, it says PDF, but then links to a document. So. These things happen. Final exam schedule. Tuesday, 10 o'clock class, our official exam schedule is Tuesday at 5:02. But then there's, if you. Class meets. Basically, you and David can't have a conflict with Thursday because all the other classes that would normally be taking their finals at the same time slot on Thursday. Conflict with this time slot. So basically we'll have our choice between Tuesday and Thursday at finals week. So be thinking about that, we'll decide on something probably next Tuesday, okay? All right, then let's talk about condensation reactions. So the rest of this chapter is still more alpha carbon chemistry and more kind of this real specific situations. We did A and B and A on Tuesday. So I'll give you a couple minutes to look at C and D and then these stabilization reactions, and then we'll go through. I gotta move my markers anyway. Placing condensation, again, it can probably be helpful to redraw this out as an ester so we can see. Where's the alpha carbon? So. Here's one of your alpha carbons. This is the compound that's we're actually adding to, because this had to have our leaving group on as well. Right, so there's our new bond. That's our new bond. We had to start with. And then the rest of the material. 1, 2, 3, 4, 5, so. Which one of those are we going to want to make it enolate with? You may enolate with. Hexanoate. And hexanoate. Yeah. Yeah, because that's one that stays as the ester, so we have to make the ethanoate there so that it can attack there. All right, so with that little bit of review. There's our new bond here between the alpha carbon and the carbonyl carbon. That's, I guess, we're gonna start by drawing one that we're going to depropate. So that's gonna give us our enolate, then we add this piece as the methyl ester.
Thumbs up.
The methyl benzoate.
Yeah.
So we start with cyclohexyl ethanoate. And LDA to turn into irreversibly turn into the enolate. Add the methyl benzoate. Here we go. So a pretty powerful tool for linking all these condensation reactions, especially when we can do them reliably and irreversibly. Pretty powerful tools because that means you don't have to do all your synthesis with the entire molecule.
We just make them together.
Yeah, get into those pieces of molecule.
So yeah, we talked about like pharmaceuticals, so.
Definitely, especially what you'll do a lot in pharmaceuticals is you'll have like a bunch of stable intermediates that you can then put together. And it's okay, well, we're gonna take A and C today, we're gonna have to do phase of condensation. We're gonna take A and D, we're gonna make, have to do phase of condensation. So yeah, it's really makes it kind of plug and play. Let's do one of these cyclizations, which again is going to be the same reaction. So and if it's symmetrical, it doesn't really matter which of these we take. We're going to deprotonate one of them to turn it to the enolate, which then attacks carbonyl carbon on the other side. We're drawing the mechanism, we want to make room there. So we're going to get a 1, 2, 3, 4, 5 cycle. And on carbon, sorry, no weird spot. Go there, 1, 2. So the second carbon is going to have, yeah. And then on carbon 3, it's going to turn into our ketone because we're going to eventually kick off the oxy. And then 1, 2 carbons, the second carbon has nothing on it, and then the carbonyl carbon. So I think that gets everything in the right spot.
Yeah.
Same thing down here. So 1, 2, 3, 4, 5, 6 carbons. Well, this carbon 1, it's got the ethyl ester. Attached to it. Carbon 3 then has 2 methyls. 4, 5, 6. Carbon 6 And so we still wind up with a beta oxo ester. It's good. There's your alpha carbon, there's your beta carbon.
So it's not symmetric. Which one would be the leader?
If your leaving groups are symmetrical, then it's not the leaving group you need to worry about so much as are you making an intermediate that's more stable one way? I realistically, I think for most of these. Trying to think of a case where there would be a notable difference. 1, 2, 3, 4. So yeah, that's a. If there's anything that's gonna make one of those alpha carbons more acidic than the other in terms of electron withdrawing group. Or electron donating group. So maybe we put, if we had a methyl group there. That's an electron donating group, right? So electron donating group
Is going to make it.
is gonna make the intermediate less stable. So that should make this one more acidic.
Yes.
So then you would get this. Would be your kinetic product.
That's what I was.
And realistically, like, especially with something like a methyl group, it's not that electron donating. So you're probably just still gonna get a mixture of the products. Especially since our products in this case don't have a big degree of. A big difference in stability. As far as like thermodynamic stability, we're gonna talk about thermodynamic versus kinetic. I think on the next slide, we really see that more in the aldol condensations because you get that alkene as a product. And alkenes definitely have rules for thermodynamic stability, but we're not gonna make an alkene here.
Yeah.
So I don't think we're really gonna see too much of a difference. As far as thermodynamic versus kinetic, so we can just go kinetic product being favored. Alright, so if we don't want to do one of these condensation reactions where the enolate reacts with another carbonyl, we can just use the enolate as a nucleophile and have it go through an SN2. So this is actually the simplest way of adding an alkyl group because you basically just get the alkyl. You don't have any other functional groups attached to it. So we start with LDA. LDA is just going to form the enolate, which then just goes through an SN2. So practice drawing that mechanism. So I'm just reminding myself of the structure of LDA, so I don't visit. So LDA stands for lithium diisopropyl. So just so we know what we're looking at, it's just a nitrogen with a negative charge and two isopropyl groups attached to it. For the sake of drawing this mechanism, we just have activities of this. So then we get phenolate. It's a symmetrical one, so for the sake of all the white board space I have over there, switch to the other side. Then we just have an R group with a leaving group attached, it's called bromine. Let's just say it's not really bromine. So great for SN2. That number of attaches. Obviously, if it's SN2, we do need to pay attention to stereochemistry a little bit. If we're our leaving group is on a stereo center. But nothing we haven't seen really. Right. If anything, this is easier than the rest. Nothing's condensation reactions.
You got a lot easier, yeah.
And then the interesting thing about this is it does give us a stereo or a kinetic versus thermodynamic control situation. And because if we wind up, if we look at the kinetic product, the kinetic product is all about how do we make an enolate that doesn't have an electron donating attached to that partial negative. But the thermodynamic product is the one where you make the more substituted ion. So that's a competing reaction if we have an asymmetric ketone. And so, a reminder about kinetic versus thermodynamic. High temperature favor kinetic or thermodynamic? High temperature means everything's got enough energy to go back and forth as much as necessary until it gets to the lowest possible energy state. It's going to be favor. We're going to, at low temperatures, we don't have enough energy. The idea with low temperatures is we have enough energy to go forward, but not back. Or forward and back, but not enough to go over this larger barrier. So as long as we keep it under a certain temperature while it's still reacting, we'll only get the kinetic equilibrium. So in the way we kind of just use generic, we pick convenient temperatures for the sake of showing this. Convenient in the lab sense. A little bit better there. So we do reversible enolate formation at -78 Celsius. which doesn't seem like a particularly convenient temperature. Unless you know that that's the boiling point of dry ice. So you do an acetone bath with dry ice in it. But acetone is still a liquid at that temperature. So that's why -78 is a convenient temperature. Happens to be, if you want to do a bath for something colder than that. Typically, I think you have to go down to liquid nitrogen temperatures, so -200 Celsius. There's not a great. If you could do boiling points. You can't do. You could probably do an ethanol ice bath, frozen ethanol. In ethanol. It would be frozen, yeah, so you could use, so the same way we do ice bath with water ice in water. You could probably do something similar with frozen ethanol in ethanol bath. And I think that that's somewhere around -30, -40 Celsius. But that's not really common for the time. We need to get below 0 at a consistent temperature, dry ice and acetone, it's almost always what's used. Versus 25 Celsius. And once we lock it in at that temperature, once we make the irreversible enolate formation, we don't need to worry about keeping it at that temperature necessarily. Because if we're doing this irreversibly, then we just need to make it enolate, and then it'll stay in that form. If we want it to be the kinetic or the thermodynamic product, you can just do it at room temperature. And really, I think you could use LDA here, but for whatever reason, they have it listed as sodium hydride. So maybe there's a lot of consideration that I'm not thinking of right now for some reason why I use sodium hydride at high temperatures and LDA at low temperatures. But I think they're interchangeable, as it's more the temperatures that matter. So it's just one factor we have to keep in mind. One of the reasons why that lab, thermodynamic versus kinetic control, was so valuable is because it does show up as a useful concept. So let's practice. A bunch of asymmetric ketones. Alright, so. Low temperature kinetic product is the less substituted. Phenolate. And a little methyl iodide, we're just gonna add a methyl group. On the end. Sodium hydride at room temperature. Make more substituted phenolate. We're attaching it to a benzyl carbon. Just to make sure you count your carbons with this one for sure. It looks wonky. And as far as naming this one would go, I don't know if it's the IUPAC name, but we do have a shortcut. And so if it was just a benzene ring directly attached, we name it as a phenyl group, right? If it's this carbon attached, then we could do something like in parentheses a phenyl methyl group attached. But the other thing is if we have this entire group, we name that as a branch, a benzene ring with a methyl in between the ring and where it's attached is called a benzyl group, BENZY. So we could name this 2-methyl 2-benzyl cyclopentanol. I don't think that's the IUPAC name. I think that's like naming a complicated branch, say isopropyl. Let's see what the IUPAC name. I'm guessing the IUPAC name is going to be 2-methyl 2 parentheses methyl phenyl or phenyl methyl. Did you get it built yet?
So it says two benzyl, 2-methyl cyclopentan, 1.
So that's putting that.
It's just the one,
Yeah.
Okay.
So they did say using benzyl fits.
I mean, that's a systematic game.
Yeah. So
Okay, well, that's good.
yeah, if you wrote it like this, nobody's gonna second guess you.
Because it's the same thing.
It's the same thing. This is just a more systematic way. If you are unaware of that example. Alright, so this one's not asymmetric yet. So we start, so after first step, we added an ethyl group, off the carbon. And then we did it at low temperature. That's gonna favor the less substituted. Gonna be on the other side, and we're gonna add a methyl. This is a pretty handy way to be able to build up your carbon skeleton however you need it to be. As soon as you put a carbonyl in there, then we can do this however we need to, because we can make we can brominate things, we can do that parallel track of.
But if you don't want the ketone there, you can always just, then we can reduce it, and if you get juice it, let's get rid of it.
Exactly. So
Pretty easy.
it is pretty easy, as long as you have a good stable of alkyl halides, right? Which is one of the reasons why we spend so much time on how we make the alkyl halides. Because now we can use them to do all this other stuff. Alright, let me double check. So there's a total of 23 slides today. Not today, left covering this chapter. And that was 7. I think my goal is to get through.
It's been 40 minutes.
It's been 40 minutes. My goal is to get through 15.
Right.
So I think now would probably be a good time to take a break. And then we're gonna talk about some other specific synthesis reaction when we get back. All right, so let's do 10 minutes. Let's come back at 5 till. Okay.
Yeah, actually, they did not send me the list. I don't have that. I feel, but they're not sending it. They're not. I think. I get it. I know that. I didn't mean that. You're gonna need one. Yeah, me and Everett was talking about it, rooming together, so.
Nice, get that squared away for next year.
Yeah.
Good deal. All right. So a couple. There's a couple more named reactions that we're gonna go through, and then we'll be done with this chapter. So as with most named reactions, they tend to be pretty niche. The one, and this one is not a named reaction with the person's name on it, it's just called melanic ester synthesis. And this also winds up being pretty useful, the net reaction here, just as long as we have an alkyl halide, we can replace the halide with two carbons, one of which is gonna be a carboxylic acid. So it's a way to add two carbons to an alkyl halide. It's kind of similar in that regard to using the alkanide ion, remember the deprotonated alkynes?
Oh.
It's a little bit similar, except that we get a carboxylic acid instead of an alkyne as our result. And it works, the reason it's called melanic ester synthesis is because, so melanic acid is that molecule there. So having that diacid with a doubly stabilized alpha carbon means it's pretty easy to deprotonate that. We've seen examples of that. And the other things that we get out of this, so this is basically just going to be an enolate acting as a nucleophile. The advantage that we get though is that after we add one, we can use a pretty weak acid or weak base to do that because it's doubly stabilized. And then we can hydrolyze the esters to make it back into melanic acid. And when you have what's called let me make sure I get the term right. The beta dicarboxylic acid. So melanic acid is an example of a beta dicarboxylic acid. Even if you've got two carboxylic acids, alpha and then beta. If you heat those, you can decarboxylate one of those acid groups, basically drive it off as CO2. So it makes it so, if you've ever heard of the term decarboxylation, it does show up a fair bit both in pharmaceutical chemistry and in biochemistry.
Like food chemistry.
And in food chemistry, yeah. Anytime you make something, a lot of times you're going to wind up with decarboxylation there. Maybe not organic ones, like in the case of baking powder, that's technically a decarboxylation when you heat it, and you generate those. You generate the gas there.
Right.
That's usually calcium carbonate. When you heat it, you drive off the CO2 and you just get calcium oxide. So that's technically decarboxylation as well. Anytime you heat something and you make CO2 out of it.
Right.
And so, and then that gives us our net result of we added two carbons, the second of which is an acid. See the term a lot in cannabis as well. Right. You're trying to make it psychoactive. THC, you have to decarboxylate it. And that's really the same exact reaction as this. So overall, the reaction is just make the enolate does an SN2. You can actually do this twice because there's still another alpha carbon or a hydrogen on the alpha carbon here. Once you're done doing it, you just hydrolyze it and turn from the esters into the acids, and then you just heat it. And the mechanism for that heat, it's with decarboxylation is the reason it works best with beta dicarboxylic acids is because you get this six-sided intermediate. Based on, and this still has all the same resonance, this is just a different way of drawing it, right? It's still a beta dicarboxylic acid. And you can effectively break the sigma bond here between the carbon and the acid group and make a CO2. So you, and then you wind up with this ethanol, I guess, so then it rearranges itself back to being a carboxylic acid. And we can show that as well, the tautomerization here to go from the enol to the carbonyl is gonna, if it's an acid catalyzed, then the first, or if it's base catalyzed, then you're just gonna do the same enol formation we've seen before. Or actually just draw it that way. So then we're gonna get the enol temporarily. And then as long as you have a proton source. Right, so that's the same enol, it's undoing the enol formation. We go from the enol back to the acid. And because this reaction generates a gas molecule, which will leave from the system, it's pretty much irreversible. The tautomerization is technically an equilibrium process like we've seen. It's going to favor the carboxylic acid form pretty heavily. But this is not equilibrium, making it irreversible. Yeah. So if we want to use this in synthesis application, we basically look at what's attached to the alpha carbon. And those are going to be the alkyl halides that we use to attack the melanic, or we use the melanic ester to attack those. So, for instance, we started with these two molecules. We started with melanic acid. And we, melanic ester. Ester works better than the acid because then you don't wind up with other nucleophiles getting in the way. So the first step is you make the enolate, and then you have to attack one of these. And then we wind up with an intermediate that's going to look like benzyl group attached. And if we then expose it to more of the base, we can make the enolate again. It still has that. It still has one alpha hydrogen. Or one hydrogen on the alpha carbon. And then you expose it to the second alkyl halide, which goes through your leaving group leaves, SN2 process. One, two, and then cycle benzyl. And And once you get here, we can't do it a third time because we're out of hydrogens. So even if we wanted to, we couldn't do that. Then we can just do a little bit of acid. We convert the esters to acid form, and then we just heat it, and we get decarboxylation. So that final product is gonna look so we're gonna have one carbon in the phenyl group, 2 carbons. Right, so
it's just one of those esters basically just popping off through the.
exactly, and the other one is converted back to the acid. You can't decarboxylate an ester, so you have to have the acid first and then. Yeah, so it's, you can make relatively complicated looking molecules. Again, having a good stock room full of alkyl halides means that we can use these in a lot of different ways. And we can do this one. The other advantage here is over just doing the ketone approach, because we didn't have to use LDA or sodium hydride. So sodium ethoxide is a lot nicer of a reagent to work with than LDA or sodium hydride. So it's basically, it's a lot. They say it's more green. There's less energy involved in making it because it's easier to make sodium ethoxide. You don't need to worry about, you're not generating hydrogen gas from it. Which again, at the scale in the lab, generating hydrogen gas is no big deal. We just pump it into the fume hood or we'll burn it up ourselves. But if we were trying to do this at an industrial scale, that starts to create a problem. Because now you gotta do something with it, and you gotta capture it.
Especially if it's at like a high amount, like
Right.
generating that much gases.
Exactly.
Ideal.
Which it is something that, so you can do, they see this a lot in engineering where your byproduct winds up being another product, actually with the Arbor hot dogs. And making that, so eventually that became a profitable enough side hustle, basically. So if you could capture the hydrogen and put it in canisters and then sell it to people, that offsets some of the costs, but that is another expense you have to do to start out. Like you have to plan for that when you build.
You have to have your capital.
You have to have the capital. Right, so there's if we wanted to add 3 carbons, there's a variation on this called the acetoacetic ester synthesis. So ethyl acetoacetate is just when you have a beta ketone relative to an ester. Which, and we can make this pretty easily because we can actually make this from a Claisen condensation, right?
You can, yeah.
Because you wind up with the ketone, there's your alpha carbon, here's your other molecule. It's actually the product that you get when you allow acetone to go through, or sorry, when you allow ethyl acetate to go through Claisen condensation with itself. So it's a pretty easy compound to make using the same concepts we talked about, and that gives you that same doubly stabilized alpha carbon. And once we have that, we can deprotonate it pretty easily and use it as a nucleophile. Just in this case, our the third step rather, is the same as before. We're going to take the ester, add heat, and decarboxylate it. With it not being a diacid. Obviously, decarboxylating is gonna look a little different, but it's gonna be kind of similar in that you're gonna start by making the enol form, and then it's gonna rearrange, the enol form will rearrange. And because your intermediate is gonna look like. Make sure I put it in the right spot. Rearrange that. You see, you can still get that if we take the intermediate and spin everything the right way, so the hydrogen from the carbonyl, from the carboxylic acid is pointed at the ketone. We can still wind up doing that same intermediate. So then that's gonna allow us to lose the CO2. So then CO2's gone. We wind up with. Wind up making this, that counts all the carbons, right? Plus that 1, 2, 3, missing one, so.
Yeah.
One, two, there's our double bond between carbon 2 and 3, yeah. Same principle, I just counted wrong, right? You get the CO2 popping off. Made the enol, which we know then is gonna rearrange back into being ketone form, prefer, yeah. Right, so the net result of this one is by using the ethyl acetoacetate instead of using the malonic ester. So we add 3 carbons and we get a ketone instead of adding 2 carbons and getting a carboxylic acid. Different uses for each of those depending on what you're trying to make, obviously. Yeah. Sometimes it's kind of handy to have a reaction that allows us to add 3 carbons instead of, because the other ones, both the alkyne addition and the malonic ester synthesis both added 2. So being able to add an odd number of carbons can be kind of helpful too. It's another tool in the toolbox, right? Yeah. All right, some practice with both of those. The malonic ester synthesis was adding 2 carbons. The second of which is an OH group, so there's the bond we're making. In the part that's not part of the malonic ester, you just have it as the alkyl halide. Usually bromine easiest to work with. Really, I guess suppose we're showing this properly. You should have the malonic ester first. First step is LDA, or actually no, we use LDA. is sodium ethoxide. Followed by our halide. Followed by acid. So the same malonic ester synthesis and actually acetoacetic ester synthesis, they're always gonna have the same form. It's just what do you put in step two? And do you do it twice before you do the decarboxylation? So here's one where we have two things added to the alpha carbon, so we've got to do it twice. It's gonna be this is as one of our substituents, and then we're gonna have just methyl iodide as the other one. And then that's it. This case makes it easy when it's symmetrical, so you just use two stoichiometric equivalents of the same thing. So purple iodide probably, maybe bromide, I don't know which one's solid. And so we were writing that out. Oxide, two equivalents of propyl bromide, then actually you would need to make sure you use two equivalents of the sodium ethoxide as well.
Make sure everything's.
Because you've got to deprotonate it twice, right? But you shouldn't. You might have to do that sequentially, even though it's the same one, just because you can't deprotonate both protons at the same time.
Yeah.
If you did it as a one-pot synthesis, which I'm not sure you can do, I think you need to irreversibly make a phenolate first, and then add this, so we would have to do it in 5 steps. Then acid.
I love the second part.
It's easy enough when they tell you you're supposed to use melodic ester synthesis. Like most things, it's when you get the blank piece of paper with no direction and you have to design your own process, that's the trickiest part. And remembering that you have this as an option can be tricky because we've got so much rattling around in our heads now. Move the other ones up so that we can put those. The acetoacetic ester gives us that group added. So that means what's remaining, these are halide. So you need to start with ethyl ester, beta keto. And then expose it to sodium ethoxide, it's deprotonated. And this one, we don't have a whole lot of flexibility with our base because we need, just as we saw before, we need to use the same base as the group so we don't get side reactions. Or the side reactions give us the same product, sorry, rather. Then follow it up with passing. Similar thing here where we can do it twice. As soon as you recognize that you have this group with a couple of things attached to it, that's gonna be your key. Do aceto, acetic acid ester, and same with this. As soon as you recognize you've got two carbons with and second one's a carboxylic acid, that's gonna make it more efficient to do malonic ester rather than the aldehyde. Right, you could still get to this using an acetoester synthesis, but it's not gonna be easier. Right, it's all about taking the fewest steps. So for B. And 1 NaOET. 2. Do the ethyl iodide. 3 NaOET. 4 we'll do benzyl bromide. Acid. This is definitely a case where sometimes working backwards can be helpful, because we don't have this in the stock room. We probably have this in the stock room. Yeah. If not this in our actual stock room on our list of common reagents we could order if we needed to. We might not have that, we might need to make that ourselves. But if we have toluene and NBS, we can make this. That's, yeah. Right, so it's a case of, okay. If I'm trying to make this, as soon as I can recognize that I have this piece. And I work out, well, I don't have that, but I know how to make that. It just breaks up your synthesis process into smaller problems. Right, and that's really why we work backwards in synthesis process. It's a little bit like doing one of those complicated conversions from back in Gen Chem, right? You might not be able to see the whole process to go from, you know, I don't know, whatever, like that black hole problem.
Oh, yeah, I remember that.
Right, like, as soon as you break it up into, well, it's just a density problem, so I just need a mass and a volume, then it seems a lot more reasonable. Like, oh, I know I can get the mass this way. So it's same thing with synthesis, you just need to break it up into the chunks.
Yeah, it's like a friggin' sauna.
I know.
No, that thing is even a roll.
I mean, I can feel it blowing out into the hallway, but it's still like,
It's gotta be helping
How
to some
hot?
extent, but
how hot is it? You have a.
I don't know, it's great.
I mean, it feels good, like, right?
It's better than we've had worse.
No, we've had worse. There was a few times where I was like quite literally like sweating.
Yeah,
Yeah.
I mean, I feel you guys. Alright, I'm gonna go over the retirement party.
Okay,
And
where is it
cut
over
some
at UC?
Because it's Jamie's birthday today too.
Oh,
So our retiree is also having a birthday today. So we've got her a dozen roses to do what else to do. Happy birthday, happy retirement, all the feels. Okay, so I'm
all right.
gonna.
You know what, I think we're gonna end there anyway, because I know I said slide 15, but slide 15 leads right into 16 really neatly. So I'll pick up on Tuesday.
That sounds good.
Jeff caught me after the meeting just now to say you didn't have to go to 4 o'clock today. You have a lot going on and a lot on your plate, so he just wanted to make sure that you were invited this time, since last time Shaker forgot to invite you.
Yes,
So
I
he
saw
wanted
it.
to just make sure that you knew
We'll be able to make it.
there was a 4 o'clock cue, but he saw the look of panic on your face apparently and was like, Laura, he doesn't need to come if you
Got a
can.
lot going on.
So I said,